Monday is not a review day. Remember, we're trying to squeeze time here a little bit. So I do want you to know on Tuesday next week, we're going to do a normal quiz day where I'm not going to be lecturing at all on 17 to try to squeeze time there. It'll be a normal, you can ask questions or work at the first part of the hour, and then the second part of the hour will be the quiz on Tuesday. Okay? So tomorrow we'll do a lab. This will be the last lecture from this chapter. This is where we ended yesterday. We were talking about Hess's law. And this was a very simple example in which we just need one of these turned around and then add them together, and you're going to get that target equation. Now, the next example that I give you is not going to be as obvious as the first one. This one is not terribly difficult. None of the Hess's law problems are real tough. As long as you try to invest and do them. I think that even though you may grapple at first with one or two of these, once you see how to do it, it'll become pretty easy. So given these two equations, could you use them to come up with this equation? And then ultimately, what is the delta H of this reaction? If you only are given that information. So I'm going to give you a moment to write that down if you want to write it or if you need it. And then we'll do this one together.
So currently he's writing it down.
Okay, this is the guy that you can blame if you go crazy by the end of this video. Thanks, Raul. Oh.
Who's the crazy one now? There you go.
When I have a Hess's law problem, I'll take a look at what the reactants are and take my given chemical equations and try to get them so that they have these as the reactants. When you only have a couple of given equations, usually that's all you need because the products will just fall together. When you have several equations, like I'll show you examples in the book where they are not as simple as this. But sometimes you'll have to do a little bit more work than that. But for right now, my beginning is always getting 2 moles of this reactant and 6 moles of that reactant. Just get the reactants worked out on the left side. Now what makes this problem easy is that I'm looking for N2 to be on the left. There's only one term that has N2 in it, anywhere, and that is in the first equation we have a half N2. So I need them to look like this. It's got to be 2 N2s. Right now, I've got an N2 on the right side, but it's got a 1/2 coefficient. So what are we going to have to do with equation number 1 to get 2 N2s on the left? Turn it over, and then multiply by 4. Right. You got the 1/2, it's got to be multiplied by 4. So I'm going to have to take this whole equation. Now by turning it around, it's going to have a negative sign in front of it. That means I've got to turn the reaction around, and then the 4 is what multiple. So that's going to give me the 2 N2s on the left. I also need 6 waters on the left. Now I only see one water term, and that's right here. So that means this reaction is going to have to be turned around. I need a 6, so that's going to have to be multiplied by 3. So second reaction, yeah, we're going to flip it so it's a -3. So let's go ahead and do that. I'll do that at the bottom under here where there's room. Flipping and multiplying by -4, well, multiplying by 4. It's going to be 2 N2s. That was what I was hoping for. But I also have 3/2 times 2, which is 6 hydrogens. And that's going to yield 4 NH3s. Now this thing should still be balanced, although not the same coefficient, still balanced. The bottom equation, I've got to turn that around too, so the water's got to be on the left, and it's got to be multiplied by 3, so it's going to be 6 H2Os. I always try to line up my arrows on this so I know what's on the left and what's on the right. And that's going to yield the hydrogen plus the oxygen. Times 3, it's going to be 6 hydrogens plus 3 O2s. All right, now what do we notice? First of all, I guess, let's find the new delta H's of these reactions. We were given the delta H, but then we manipulated them. So we've now got to multiply this thing by -4. And that's going to be -184. this thing, we've got to change the sign to multiply by 3. That'd be 1,500 minus 48, 14,452. Positive. So make sure that you get the signs right. We did have to turn that thing around, so it changes the sign on the delta H, on both of them. And let's go ahead and add these two together. We know that by Hess's law, when you add two equations together, when you add their enthalpies together, the two reactions, that'll be the overall enthalpy of the final reaction. So notice we've got 6 hydrogens on the left and 6 hydrogens on the right. Those can cancel out. And what we're left with, 2 nitrogens, 6 water stones on the left, 4 NH3 CO2s on the right. So we've gotten the equation that we want. Just add these two together, and notice it gives you 12 something, 1268. Positive. That's Hess's law. It's not bad. What's that?
Feels like a redox.
It is. That's the way I feel. It just kind of all falls together. Now, I'll warn you, they're not all simple like that. There's some problems in the book that would involve redox. That involve redox. That involve Hess's law. Number 72. Let's see if I can turn the light on. Here's number 72. You're given 3 equations, 1, 2, 3 here, and then here's our target equation. So you're going to have to manipulate these equations. So you have ClF and F2 on the left, and ClF3 on the right. You'll probably need all 3 equations. Sometimes you don't need all of them. One of them just be there as a distraction. But I think in this case, all of them are needed. 73, same thing. You have 3 equations given. You have a target equation. You have to get to this. Manipulate these so that they add together to get there. 74, same thing. You have 4 equations now given. 75, you have 5 equations you have to come up with. So you can see that they would get progressively more complex.
So just system of equations. It's so easy.
Yeah. That's all it is. That's it.
Do we use all 5 equations?
I think in that one you do. Use all 5. Yep. Yeah. Now, let me show you another one. I think this one is just important to look at. 112. Okay, we're right there, 112. Take a look at number 112. And I don't know if 112 is assigned. I didn't look. But it's not so easy. Using the following data, calculate the standard heat of formation of ICl in kilojoules per mole. So it doesn't give you a target equation. It says, given these 4 chemical equations with their delta H's, what is the heat of formation of ICl? Anybody know what heat of formation is? Remember the day that I introduced it, I said, note this definition, it's important.
Oh.
What is it?
Is it the amount of heat, like energy you have to put in to get a reaction to start?
That's activation energy,
Oh.
not heat of formation.
QW.
You know that the data table in the appendix, page A19 that we looked at the other day, that was the heat of formation table. You remember what the definition of heat of formation is? Okay, it's the heat required or given off when 1 mole of a compound is made from its elements. Do you remember that definition that I gave you? You wrote it down, and I made a big deal of it at the time. Maybe not a big enough deal. But heat of formation is the amount of energy given off or taken in when 1 mole of a compound, like that, is made from its elements. And not just made from its elements, it's got to be made from its elements in their standard physical state. So we should be able to write a chemical equation that represents the heat of formation of ICl. So what elements make up ICl? So we have to make what plus what yields ICl? Well, it would be from its elements, iodine and chlorine. What do you know about them? They're diatomic, both of them are. So it's I2 plus Cl2. So these are both diatomic. So that equation should look like this. 2 ICLs are made. But the definition says that it's the amount of energy taken in or given off when 1 mole of a compound is made. This is 2 moles being made. So what we have to do is just take that equation and divide by 2. It's going to be 1/2 I2 plus 1/2 Cl2 yield to ICl. The delta H of this reaction is what I'm trying for. And not only that, that's why this is number 112. This is in the additional exercises section. Those can be pretty hard, or involved at least. Part of the definition of heat of formation is from the elements in their standard physical states. Take a look at this. You have iodine as a gas in some parts, and iodine as a solid in some. What is the standard physical state of iodine? It is a solid. How do you know that? Right, you're pointing at the periodic table. The color of the symbol on the elements on the periodic table tells what their physical state is. Iodine is in black up there. Like most of the periodic table is in black. Those are solids, room temperature. A couple of blue ones, bromine and mercury, those are liquids. And then the green ones up there, the far right, the noble gases, and then oxygen, chlorine, those are gases.
And what about the ones that are like bolded?
Yeah, the ones that are kind of outlined like this, those look bolden from where you're at. There's kind of a shadow effect there. Those are synthetic. That's why they've indicated which ones are not actually occurring in nature. That's them.
Well,
They're solid. The physical state would be solid. So you need iodine as a solid as a reactant and chlorine as a gas as a reactant. So you're going to have this by the end with a 1/2 in front of it as your reactant. So anyway, these are some things can be kind of challenging, but I find them fun. I like to choose. All right. I asked you to have a book at your desk because the next problem is a reaction in which we're going to try to find delta H from the heat of formation table. This looks like a chemical equation for a lab that you've recently done. The freezer bag lab. Yeah, you had a carbonate compound. Everybody had a different carbonate. You added strong acid to it. That's the hydrogen ions. And a carbonate plus hydrogen always makes CO2 and 1. So this was, if you had baking soda, this should have been your net ionic equation. What is the delta H of this reaction given the thermodynamic table? So go to the appendix in the book, and what would be delta H of this reaction?
I must have added it. I think I did. I added
We are currently doing nothing.
that.
Page A19 is where all these, I believe, are A20.